Now we want to talk about the volume of a cube. Okay, so what's the volume of this 2 by 2 cube? Now you can see both faces here, and you can see both faces in the reflection, so we can see all the dice that make up this cube. Now we don't really need to see them all. We know that there are 2 rows on the base, and each row has 2 dice, so that we have 4 dice on the base, and then we have another layer identical to the base layer, making a total of 8 dice. And of course we can count them. 1, 2, 3, 4. Oh, see what I did? I went 1, 2, 3, 4. I counted this one and then I counted it again, didn't I? 1, 2, 3, 4. And then 5, 6, 7, 8. Okay, so that we see that a 2 by 2 by 2 cube of dice has the volume equal excuse me, to that of 8 dice. So we have a volume of 8 dice volumes here. But if we say 1 dice volume is the volume of 1 dice, then we have 8 dice volumes. Now if I build this back into my cube, and I kind of cheated when I took this apart so that I can quickly do this if I don't knock it all over. I don't know how I'm going to work that one in there. Let's see. I think there's about no way, but let's see if I can do it. Okay, that'll do. Now I have a 3 by 3 by 3 cube, and rather than using a formula, and formulas are fine, but it's much finer to understand the principle behind the formulas and why the formulas work, we can see that I now have how many cubes. We can see them all except the one in the very middle. Okay, so we could count the ones that we can see. There'd be 26 of them. There's one in the middle. How do I know that? I know there have to be 27 because in the base layer I have a row of 3, and then I have another row of 3 and another row of 3. So I have 2 rows of 3. Actually, I said we could see them all, but the one in the middle, there are 2 below this middle die that we can't see. So we could actually count 25. We have to add those 2. Okay, in any case, again, we have a row of 3. Now we have 2 more rows of 3, so we have 3 rows of 3, and we know that that's going to give us 9 cubes on a layer. Of course, we could count the cubes on the top layer. You've got a row, and a row, 3 rows of 3. And I'm going to knock the whole thing over if I'm not careful. Okay, and then we have 3 layers. Now each 3 rows of 3, 9 cubes, 3 layers, that's going to give us 27 cubes. So we have 27 cubes there, and that's why the volume of a 3 by 3 by 3 cube is 3 cubed. If we wanted to build a 4 by 4 by 4 cube, we'd need a whole lot more dice. Okay, we need over twice as many dice. We need 64 of them, and you can figure that out, and you probably already did. So that's the idea of volume. And we have formula for volume of a rectangular solid. Right now, what have I got? I've got a 3 by 3 by 2. Well, you got a formula that says length times width times height, but you don't really need that formula, especially if you have whole numbers. You can understand in terms of whole numbers how it is that you get your volume just by counting cubes. Now, if you have fractional dimensions, well, if those fractions are rational numbers, you can divide the cubes up into tinier cubes and count them. That might get old counting them, for example. Well, if the fractions have a big denominator and if they're irreducible, you're going to have to do a lot of subdividing, but in principle you could do that. And you could prove that you still have the length times width times height formula. And it's a handy thing to know, but you have to know where it comes from in order to really think about volume. If you have objects that can't be built up from cubes, let's take the water in this glass, and you want to get the volume of the water in this glass. How are you going to do that? Well, you're going to probably rely on a formula, but exactly what does that formula mean? Where did it come from? And how can you adapt if you have some other shape, because not every shape has a formula that you can look up. So, that's an idea for the future. For right now, let's just think in terms of volumes, and let's think in terms of squares and cubes.